Hey everyone. So, welcome to this lecture where in the Deep Learning from Scratch series, where what we're going to do now is kind of construct in detail a single node learning model, right? And so, we've understood the basic idea of neural network in the previous lectures, understood what backpropagation is. We haven't implemented that yet, but we've understood the basic idea visually. And then we've explored gradient descent in quite a bit of detail. So we know how to train a model, right? And so now we're going to start building our first AI, but we're just going to focus on one neuron, right? And we're going to implement this. And then in the next lecture, we're actually going to train this for a regression problem, right? Okay. So the idea of a neuron, right, mathematically, um, comes from the idea of how neurons work in the human brain, right? The human brain is built up of neurons, right? And so we've already covered in the intro lecture a basic idea of how kind of neurons came across. Um, and so the idea here of a simple artificial neuron is that it takes in the inputs as a function in the neuron that operates on these inputs and it gives out an output, right? So you have multiple inputs coming in and you end up with an output for that neuron, right? Which is a particular value depending on the problem you're trying to solve. And then depending on the position of that neuron, if it's the last neuron, it would actually be the output of neural network. If it was a neuron somewhere in between, then the output would be passed to the next set of neurons in the next. Now, in this particular lecture, we're only focusing on a single neuron, and we're just going to try and see how you can solve a problem with that one neuron, a simple problem, right? And then we'll explore how more complex problems are solved by assembling neurons. So, the basic idea of machine learning and deep learning models is that they have this data available, right? And you are trying to learn a pattern in that data, right? And so, what you have, for example, in this case, is columns of data, right? And say each column represents a particular parameter. So, for example, if this was used car prices, for example, you would have a column that say indicated how many kilometers, the car has run, and so on, right? It's just an example, but it basically be a different, just different columns with different sets of parameters. So each of these would be the inputs, right, to your machine learning, in this case, deep learning model. Uh, in this case, in fact, a single neuron, not a deep learning, but in a deep learning model, right? And you'd have for each row, which indicates one set of inputs, you'd have the actual value, you know, which you can call a label, right? So we know that in reality, given these inputs, the output should be this. And what the job of the machine learning model is to understand that from this data. And so the model would be trained such that then finally, in a prediction scenario, you'd give it the new set of inputs. And what would it do? It would actually predict the output with a sensible, good accuracy, right? And so for the single neuron, let's just take those inputs, right, and say they're being fed into the neuron. And what you get is a predicted value of the output. In training, you'd compare this with the actual label and see what happens. But for now, let's just understand how this neuron works, right? And then, as we saw in the previous slide, you can then, well, right here, once we understand how a neuron works, we can then in future lectures kind of connect neurons together to get a neuron. So for this type of simple feed-forward neuron, one of the standard ways of or how this would work is you would have a linear part to the neuron. And so given these inputs, for each input, it would have a parameter called the weight associated with that input. Right? And what would it do? It would multiply that weight with that input. So you have x1, you multiply by w1 and get w1x2. You have x2, you multiply by w2 and get w2x2. If you had x3, you'd multiply by w3 and get w3x3, and you keep doing that for each of your, input features. And so for xn, you'd get xn times wn, wn xn, and for everything in between. So that'd be the first thing that is done, which is you weight your input with the parameters, and these are parameters of the neuron. These are parameters called weights that would actually be trained, right? And so that is what would be set depending on the data. Okay. Once you've got this, what do you do? Well, we know that the neuron takes in multiple inputs but returns one output. So how do we convert this into one? Well, a simple way to do this is to sum cross them. So when I say sigma I, wi xi, it's just the summation symbol, and then wi xi, the I is what is repeated. So effectively what that does is it says w1 x1 plus w2 x2 plus w3 x3 and so on till you get to wn xn. And so you've now summed all of these, which means you've gone from these input features, n input features, to one value, right? You could also think of it as n dimensions to the input, right? If it's so, you can think of it as an input vector. You have n dimensions, but you effectively got one value. What would you do then? There's another parameter of the neuron called the bias of the linear, right? And so the bias is then added to this wi. So why do we do that? Well, what if all the inputs is zero? All the inputs is zero. Wixi, sum of Wixi would be zero, right? Because the xi's is zero. So Wixi is zero. So the sum of that is zero. But what if the actual data had a value, right? What would you do then? So the bias captures that, right? Even if all the inputs is zero, this would be zero, but then the bias could capture any offset, right, associated with zero, right? So if you look at it in a two-dimensional case, you have x and y, it would be the intercept, right, of that line. You'd have a slope, which was captured here, and the intercept. So we've got sigma I, wixi plus b. What you get is what we're calling z, which is an output to the first part of the neuron, which is the linear part. And so the parameters that are trained would be the weights, and there'd be as many weights as there are inputs to that neuron, and then there'd be a bias. So you actually have, if there are n inputs, you have n plus 1 parameters, the n weights and the one bias. Okay. So for this neuron, we've got the first part. What happens next? Well, before we figure that out, we know that neurons have to be trained. And so neurons that have to be trained are trained through backpropagation. We've covered that, right? And so what we need to train the neuron is the sensitivity of a loss function, which determines the error in the machine learning model with respect to the parameters. Now, as we know from backpropagation, that's done by chaining, right, the sensitivities, across backwards, right, through the neural network. So what we need actually here is just the sensitivity of Z, right, which is the output, which is sigma I wixi plus b with respect to these weights and the bias in this case, right? And then when we train this, we'd have the next piece here, and then we'd have a loss, and we just change that. So what's the sensitivity? So we have dou z by dou w1, which is dou by dou w1 of w1 x1 plus w2 x2 plus w3 x3 and so on plus p. So if we write this out, what happens? Well, we see that w1 only shows up in the first term, right? None of the other terms have w1. So the sensitivity of each of those terms to w1 is zero, right? And so all these terms go to zero. You're only left with the first term, which is dou by dou w1 of w1 x1. Now, x1 is your input. It has nothing to do with w1. So there's no dependency there either. So you can take x1 out, and it becomes x1 times dou by dou w1 of w1. You can use product rule here of differentiation. If you're not familiar with the product rule, we've got a lecture on differentiation that we've covered, and I'll add the link to the description so you can check that out. Basically, you can take the x1 out, and you can do dou by dou w1 of w1. Now, the derivative of w1 with respect to w1 is 1, right? So what you're left with is x1. What if you do dou z by dou w2? You'd have the same kind of expansion here. The difference is now the w2 term is what would remain. Everything else would go to 0. And you would end up with x2. And so the basic idea here is for the linear part, right? And when we kind of describe this in the form of layers, it would be a linear layer in the neural network. The derivative with respect to wi, with respect to a particular weight of that neuron, in this case, with respect to the z, the derivative with respect to z of wi is xi. So if it's w1, it would be x1. If it's with respect to w2, it's x2. So we've got this part of the partial, of the derivative, right, of the sensitivity of z with respect to the weights. What about the bias? Well, simple. None of the other terms have the B, right? There's just this term, everything else goes to 0. And what are you left with? Dou by dou B of B, which is 1. So the derivative of this Z, which is just sigma I wi xi plus B with respect to B, is 1. And we can see here, right? This is all that contributes to the derivative. There's a third derivative that in this particular case we don't actually need, but in general, because we're explaining a neuron, that is useful if you're not the first neuron, you're in a middle layer or the final layer, is the derivative with respect to the inputs, right? Because you would then pass that back to the previous layer for backpropagation or through backpropagation. And so if you're taking the derivative with respect to the input, what happens? So if we take with respect to x1, what happens? Well, same, it's actually quite similar, not the same, it's quite similar with like W1, where all the other terms go to 0 because there's no dependence of x1 on any of these terms, right? It's just x1 just shows up in W1, x1. And again, you can use the same principle, but now W1 goes out, product rule, and we know that there's no dependence of a W1 on x1. So this term goes out, you're left with W1. And so if you want the sensitivity of Z with respect to the inputs, it's just a corresponding W1, right? So if it's X1, it's W1. If it's X2, it's W2. If it's Xi, it's Wi. Good, so we've got the sensitivities of the linear layer, right? Of the linear part of this neuron. We've got the sensitivity with respect to Z of the parameters, the weights, the bias, and the inputs, which we've just done. In this case, we don't really need. The second part of the neuron is what is called an activation function. And so this Z now, which is some form of aggregation of the inputs, we've taken these inputs and we've got one value from that. The activation function takes this value and returns an output, right? And we're going to call that output A. So Z is Wi, sigma Wi xi plus B, sigma I Wi xi plus B, sum over I. And then A is that Z passed through an activation function. Now, depending on the problem, there are different activation functions. Started off with the idea of a binary activation function, meaning for Z less than 0, the activation function would say 0, less than equal to 0. And when Z is 1, the activation function, well, Z is greater than 0, the activation function would be 1. So it's a simple step. And so depending on your inputs, if the inputs were less than equal to 0, your activation function would be 0. And if the inputs greater than 0, the activation function, which is very interesting, it would basically trigger the neuron if your inputs were greater than 0, right? The sum of the inputs, the Z was greater than 0. So this is kind of an early version of this. It's not used all that much anymore because it would kill the sensitivities in backpropagation, right? For any set of inputs that would result in a Z less. Another example is the ReLU activation function, and we're going to code this up in this lecture. Right? So what that does is it says, well, if it's 0, it's still, the activation function is still 0, right? For any Z less than or equal to 0. However, if the input is greater than 0, then the activation function is actually just the value of the input. So Z is what is passed in. It's sigma Wi xi plus B. The activation function is just that Z value. Now, another example of an activation function, which is used a lot in classification problems, is the sigmoid activation function. And if you're familiar with this function, it's the logistic function. So it's used in logistic regression. Right? So what that does is takes the Z and then does this function 1 plus e to the power of minus Z. And so what you get is for very negative values, the actual value of the activation function is 0. And as we get closer and closer to 0, the activation function starts increasing. And then it increases till at 0, it's 0.5, right? E to the power of minus 0 is 1, 1 plus 1, 1 divided by 1 plus 1, 1 divided by 2 is 0.5. And then what does it do? As the Z becomes larger and larger, it converges to and then is just 1, right? So it plateaus at 1. So it's basically squishing a large Z, very negative, very positive, to be between 0 and 1. And a variation of that, right, which is also used a lot, is the tan H activation. Right? And what the tan H activation function does, again, difference is now it goes from minus 1 to 1. So it's squishing Z from whatever very negative value to very positive value to be between minus 1 and 1. And as the value comes closer to 0, it kind of goes from -1, goes to 0, and then comes to 1. So these are examples of a few activation functions that are commonly used. There are others, and so we'll add more in the notes, but you've got a basic idea of what the activation functions do. Now, in this particular lecture, what we're going to do is we're going to code up a neuron with the ReLU activation function, right? And so the ReLU takes in the Z, and then if Z is greater than 0, it just gives out the value of Z. If it's less than or equal to 0, it gives out a value of 0. Now we need the sensitivity of this activation function with respect to Z, right? And then we can chain it with what we've done previously to get the activation function with sensitivity with respect to the weights and the bias. So the derivative of A, which is the output, right, with respect to Z is 1, right, because A is Z. So it's 1 when Z is greater than 0. And when Z is less than or equal to 0, the output is 0. So the sensitivity is basic differentiation, right? Good. So we've understood the basic idea of a neuron, right? We've got a quick glimpse into what a neuron looks like, and how the linear part of it takes the inputs and converts it into one value Z, which then goes through the activation function, and we get an output value. So let's go implement this neuron now, and we'll then, in the next lecture, train this. Okay, so let's go open up our Jupyter notebook and get started. Okay, so we've opened up a Jupyter notebook. Let's get started implementing this single neuron model. So a few imports. We're going to import math. We're going to import NumPy as NP. We're going to import pandas. We're going to import matplotlib, right? SPLT. And then there's this library called GraphWiz. And when we get to it, I'll show you how to install this. These two are actually for the second part, which is a different lecture, but we're going to use this same, notebook and extend it. So I've just left the imports in there. So let's get started with a neuron. What we're going to say is we're going to set up a simple class, right? And call it neuron. So this is how you write a class in Python if you're not familiar. And if you want to learn the basics, if you're not familiar and have never written code in Python, we have a Python for Beginners series running right now, actually. And I'll add the link below so you can use that to get up to speed. So the init function initializes this the object when we create one for this class. And what are we going to take in? We're going to take in the weights and the bias, values for the weights and the bias. I'm also going to take in a tag, right, which it just tells you the tag for the neuron. And so what am I going to do? Well, I'm going to print the values. I'm just going to say and I'm going to say give it the tag. So what are we going to do? We're going to say self.tag, and so this is the data associated with the class. The class is data. We're going to say self.tag is equal to the tag passed in. And what are the parameters of the neuron? We have the self.weight, so it's the weight passed in. And then we have, and what I'm going to do is I want to make sure that what's passed in, I'm going to pass in a list of weights. So I'm just going to say np.array, and what it will do is take the weights, which is a list passed in, and convert it into a NumPy array. I'm going to say self.b, which is the bias, is equal to the b passed in. So for now, let's just leave that there. And so what am I going to do? I'm going to initialize it. Let's just start. So I'm going to say neuron 1. So let's call it, let's just call it model, right? And so the model is neuron. What are the weights I'm going to give it? So I'm just going to initialize a set of values that I've kind of chosen. So I'm going to give it 2 weights. I'm going to say the neuron has, at this point, 2 weights and a bias. And so we're going to say we're going to give it 2 inputs, right? We're testing with that, and the problem we solve we train the neuron on is actually going to use, have two inputs. And so 2 weights. The bias I'm going to say is 0.1. And the neuron, I'm going to call it N1. So let's just run this once so that Python notes that's there. Okay, so it says when I'm running the model, it says init neuron N1, right? Very good. And actually, if I just print, just to check if I print model dot w and model dot b, what do we get? We get 0.2, 0.3, and 0.1. Good, which is what we've passed. Very good. So what's the first thing we want to do? We want to set up the forward pass, right? Now, so what's the first thing we want to do? We want to set up the forward pass for the neuron. So what is the forward pass? So let's just define a function in that class, and we're going to call it def forward, right? And what is the forward pass going to do? It's going to take in, so self indicates it's a function of that class. It takes in the self object. And then what is it going to do? It's going to take in the inputs that you want to run the forward pass on. So I'm going to call it x, and x obviously should have two dimensions, right? It should be one dimensional. It should have the inputs, right? X1 and x2. So it's going to take in self.x, right? And then what do you do? Well, you say, what do you do first? Well, sigma I sum wi xi. So let's say z is equal to, and how do you implement this? So there are two ways to do this. Simple one is to say self.w, and I know two inputs, so x0 plus self.w1 into x1. This is the naive way to do it. Now, if you know you have two inputs, this is what you can do, right? If you don't know, what you could do is create a loop over the size or the length of the x and do this. We're going to do something simpler. We're going to say, well, we know numpy has a simple function called numpy.dot, and if you give it self.w and x, what it does is computes a dot product, which is effectively a dot product is w1 x1 plus w2 x2 and so on. It does it for as many dimensions as that. Good. And then there's one more piece to this, plus b, right? Self dot b. So you've got your sigma wi xi plus b. What's the next part? It's the activation function. So I'm writing these comments here just so that when you look at this code, you understand what's happening. So we have said that it's a ReLU activation function. So what's the ReLU activation function? Well, the ReLU activation function says that if the input z is less than equal to 0, then the output A is 0. If the input is greater than 0, the output is the input, right? Now, this is an interesting way to implement this. You can just say A is max, right? 0 and z. What does that do? Well, if A is less than or equal to 0, z is less than or equal to 0, then max of 0.0 and z will give you 0, right? And if z is greater than 0, then the maximum of 0 and z will be z, right? Because it's a positive number now, and you get A. Good. And that's it. That's a forward pass, right? Very, very simple. Now we're going to do one thing. We're going to store in this neuron so we can visualize it. We're going to store, and also for back propagation, we're going to need it. We're going to store the A. So we're going to say self.a is A. I'm going to say self.z is Z. We're also going to store the input self.x is X. And so here, I'm just going to add these. We say self.a is none. Self.z is none. Self.x is none. You could also say it's 0, but I'm just going to leave it as none. Okay. And set. What do we want the neuron to return? Even though it's just a single neuron problem, we're going to say I want to return the output. So that if you have another neuron or you add a loss function to it, you can pass it. So what's the output? It's good. So we've just defined the forward pass. Let me just add a comment here that says forward pass to the neuron. So it's really simple, right? We've just done sub sigma I, wi xi plus b, which is the linear part. We've passed that z through the activation function, which is a ReLU activation function. So let me just write that ReLU activation function, right? And what does that do? If z is less than equal to 0, then the maximum of 0 and a negative number is 0, right? So it will give you 0, which is what we say it is. On the other hand, if this is a positive number, the maximum is the positive number, it will return z, right? So which is the ReLU activation. So what it's doing, why we're using a ReLU here? Well, one, you see how an activation function works. Two, in the problem we're going to solve, we're just saying that if the sum of the input times the x is less than 0, just cancel out that, right? Okay. So what do we do? Well, let's call the forward. So we've already set up the model here. We're going to say model. First, we need to define the data. So let's say x, let's set up an x, and I'm going to say np dot, I'm always going to use np dot array so that when you do these dot products and stuff, it's using numpy arrays, right? So what's the input I'm going to give? Let me just check the value I've set up, right? So that, I can validate what's happening. I'm going to say it's 0.2, 0.1. And so what are we going to do? We're going to say model, which is basically this neuron dot forward, and I'm going to pass in the x. Let's run this. And the mistake I've made is I've not rerun the neuron cell. So Python or the Jupyter notebook doesn't know there's a neuron function has been added, a forward function has been added. I'm just going to create the neuron, printed it, and let's see this. Good. So we've got the answer of 0.17, right? Which is good. Well, how do we know it's correct? 0.2 times 0.2. So we can just check this here. We're going to say 0.2 times 0.2 because the input is 0.2. And what were the weights we had passed in? We had passed in 0.2 and 0.3. So 0.2 times 0.2 plus 0.1 times 0.3, right? Plus, what's the bias? The bias is 0.1. What do we get? 0.17, right? Good. Okay, so let's now write the backward pass, right? We've already done the forward pass. We know it works. Let's write the backward pass. So what are we going to do? We're going to say, we're going to define a function in that class. We're going to say def backward and self, right? Because it belongs to that class. And then what are we taking in? Well, so single neuron model, which means the next function is the loss function, right? The next neuron or the next node is the loss function. The loss function is basically computing the error and it's taking in the output from this neuron, right? So once it takes in the output from this neuron, it returns the sensitivity with respect to the output, right? Because the output, the input to the loss function. So the loss function basically would be something like this. When we'll set it up in the next lecture where we train the model. So I want to keep the loss there, but it basically takes in the output, right? A, which we also call y hat, and it takes in the actual label y and it returns the loss value, right? And what it also returns, or what we need is dl. What it returns is dl by dA, the sensitivity of the loss with respect to a, which we can then propagate through this neuron or back propagate through this neuron and get the sensitivity with respect to the parameters that we want to train, right? Which is the weight and the bias. So what happens? We get dl by dA that is passed in. So what do we do? Let's write out the steps. So we'll write the step by step like we defined it in the theory part, right? A few minutes ago. So the first thing we need is we need dl by dz, right? Which is the previous thing. So dl by dz is dl by dA times dA by dz, right? Because as we know here, A is basically directly dependent on Z. So what do? We first set up dA by dz. What is dA by dz? Well, in this case, the output A is equal to Z, right? If Z is greater than or equal to, well, it's greater than 0. If not, the output is 0. So we can say, well, let's just say dA dz is 0, right? This is not the complete part, right? So we're saying, well, just initialize dA dz to 0. Now what happens is Z is greater than 0. Then the output A is Z, which means dA dz will be non-zero. But we know in that case, A is equal to Z, right? Which means if A is greater than 0, that would mean Z is greater than 0. So you can use either one. I'm just using self dot A is greater than 0. Then dA dZ is 1, right? Because A would be equal to Z. So dA dZ would be 1, right? Let me just write that because A equal to Z. In that scenario, right? So when Z is greater than 0. Okay. And so dL, at the end of the day, we only care about the sensitivity with respect to the loss because that's what we want, and that's what we're going to use to train the model, right? So we only care about the sensitivity with respect to the loss of DL, and so DL dz is DL dA, which we've just passed into the function right here, times dA dz. Good. What's the next step? So we have basically gone through the activation. What's the next part? The linear part, right? So what's the linear part? What do we need now? We need dl dw, dl db, and then just to validate, we're going to add a dl dx, right? Now, because it's a single neuron model, the x is the input, right? The actual data. And so we don't really need those sensitivities. But if you were doing a full neural network and you had a neuron and it was a neuron in a middle layer or the last layer, you would need to pass back or back propagate to the previous neuron, right? In which case you would need DLDX. So I'm just going to compute it anyway, right? But we won't really worry about it. It's not really, we're not going to use it in training. So DL, DW is, so DL, DW is DL, Z, which we've just computed, times dz dw, right? That's the local derivative. And this is what we have got by back propagating, at each step and using chain. So what do we need for this? We need dz dw, right? So what's dz dw? Simple, right? We've already done this in the theory part. Z is the dot product of w and x. So it's basically w times x. So dz dx1, so let me just write that here. We just did this. dz dw1 is x1 and so on. And so dz dw is basically self dot x, right? dz dw1, the first one there would be x1. The second one would be x2 and so on, right? That will what it would be. So it's just x, right? And so we get dl dw is dl dz times dz dw. What about dz db, right? Well, we know dz db is 1, right? The derivative with respect to the bias of z is 1. We've already computed that, right? You look at this term here, the derivative of z with respect to b is 1. It's not dependent on this, and this is 1. And so dl, and so we don't technically need to use chain here, but we're going to use chain rule anyway. We're going to say dl, we're going to stay consistent and say d z d. And then what's the last piece, which is so this is and so what's the last piece? It is dl dx. So we're going to say dz dx. Again, if you remember from the theory part, it's w dot x, right? Z. And so dz dx is basically self. And so dz dx1 would be w1, dz dx2 would be w2, right? And then dl dx, again chain rule, dl dz times dz dx. And that's that. We've done back propagation, right? We've back propagated through this expression. So it's a single neuron. We're back propagating through that expression. We've back propagated through the activation function and then through the linear part. Propagation, or rather back propagation. Okay. And so this is dz dw1, dz dw. This is dz db, and this is dz. I'm just writing the comment so that it's clean, right? dz dx. And what we'll do is for visualization purposes, we're going to say self.dz. And so let's start with DL because we're going to use an interesting kind of method to visualize this. So I'm going to just store the derivatives with respect to the loss, right? I'm not going to store the local. For now, I'm just going to say that is dl dA. You're going to say self.dl dz is dl dz. Self.dl dw is dl dw. Self.dl db is dl db, and self.dl dx. Let's store it anyway. Self.dl dx. I was going to say we're not going to use it, but let's store it anyway. And what am I going to return? Well, if there was a neuron you wanted to pass this back to, we would be returning dl dx. So I'm just going to return dl dx. So we can, when we kind of assemble this into a network, 2 lectures from now, we can just reuse this. Now, if you wanted to store some other value, you can use the self dot to do that. You could also directly have used the self dots here, self.dzdw, but I like to write the code this way where at the end of it, I kind of pack it this way so that I know what I've stored. And so we also need to add these here because we hadn't set that up. So I'm just going to bring these here so that I'm initializing them. So in the event, initialize a neuron, you do it cleanly. So I'm just going to make all of them none. And then when you run backward, they get set, right? Okay. Good. So we're done with forward and we're done with backward. Let's test this out. So backward pass. And so we're going to say model.forward has already been run. So we're not running it again, but actually we do need to because we've just modified this class, right? We've added the backward. Let's recreate this neuron. Let's print it. We've got the same answer. Forward. We've tested that. So we're going to say model dl dx is equal to model dot backward. And what are we passing in? We're passing in dl dA, right? So what is dl dA? So let me just set it to be is equal to, and I'm going to pass in a numpy array just to make sure the math doesn't goof up inside. And it's going to be an array with 0.5. Right? So we're saying the sensitivity passed back from the loss function is 0.5. And let's go call this. So I'm going to print. Let's do it in the next step actually. So let's just run this first. It did run. So what did we get? So if you print dl dx, what did you get? Let's annotate this. dl dx. And what do you get? 0.1 and 0.15. Okay, how do we know this is correct? Well, let's visualize this. That's a good way to do it, right? Okay, so how are we going to visualize this? So if you remember the imports, we imported something called GraphViz, right? And so I've kept the code here because I don't want to write this whole thing. If you're interested, I can add in the notes a tutorial on GraphViz and maybe create a small video. But it's basically a really nice visualization library that makes it very easy for you to visualize plots and graphs, right? And so to install it, you can go to graphviz.org and that will help you get up and running. I'm doing this with Python. So we're using Jupyter notebooks and we have set up using Anaconda. So in Anaconda, you can just, if you're using the user interface, you can just install GraphViz and install Python GraphViz. If you're using the Conda command line method to install, you say Conda install GraphViz, Conda install Python GraphViz, right? And then as we have done with the imports here from GraphViz, import digraph, right? And so I've created this small kind of graph here. What I'm going to do is I'm going to add it to this neuron class. So I'm going to say def visualize, right? And so now it's a function in this neuron class. And that's why I've stored all the sensitivities, right? I'm just going to paste this code here. Let's just align this and then I'll show you how this works, right? So let me just align this. Okay, so we've got this. And so I'm going to say first model dot visualize. Then I'm going to say model dot viz because that's what I'm storing the dot. And so when I initialize this, let me just add again just to make sure we're clean. It's set dot viz is equal to none. I'm running that again. And let's just go back, initialize the neuron again, rerun this. We've got the forward, we've got the backward, and solutions. So GraphViz helps you create this really nice graph, right? Where you can see the inputs, you can see the first operation, you can now see Z, you can see what goes there, and you can see what happens there. Right? Okay, fine. And so there's obviously one small bug here. What goes from here to the ReLU is not W, it's Z. So let's go fix that first. Let's say this is not W, it's the edge, and the edge is Z. Right? And so if I rerun this, okay, so Z and we get Y or A, right? Okay. And so what this does is it shows us the inputs X, right? X being 0 0.2 and 0 0.1. This is the input part, and W is the associated weights, right? The bias is 0 0.1. That goes in here. And what you get from WX plus B, we already checked that is 0.17. That goes into ReLU, and the output is 0.17 because it's greater than 0. We're passing back 0.5, which is the derivative. So when that comes back through the ReLU, again, because Z is greater than 0, we've just above coded up that the derivative would be 1, right? Because Z is greater than 0. So 0.5 is passed back here, right? Okay. So we've got, this is DL, DZ, right? Okay. Now what do we do? From here, we want to propagate these three. So you want to get DL, DW, right? What would you do? 0.5 times 0.2, right? Because DL, DW1 is X1. So 0.5 times 0.2, which is 0.1. DL, DW2 is X2, which is 0.5 times 0.1, which is 0.05. So this is correct. What about DL/DB? We know DL/DB is basically this times 1 because DWX plus B or DZ/DB is 1. So this gets propagated and it's correct. So we've got the correct values for this. And DL/DX, it's 0.5. We know that the local derivative is basically, so DZ/DX is the X1 is W1, DZ/DX2 is W2. So 0.5 times 0.2, again 0.1. 0.5 times 0.3 is 0.15. So we've seen that the forward pass and the backward pass are correct. Okay, so what if I change one of these inputs, right? So what if I say this now, X is minus 0.5, right? I've made a change here. I've said X is minus 0.5. So let's rerun the forward pass. And you get 0, right? Because what this results here is you get minus 0.5 here, right? And the answer is of Z, right? WX plus B is minus 0.999, which is less than 0, which now means that the ReLU gives 0, right? And so the backward pass also, if you revisualize this, is 0 because the derivative coming in from here, the local derivative here is 0, which means this is not propagated any further back. And so because it's not propagated, the values become 0. So we see that our neuron does a pretty good job. It works for the forward and the backward pass. So what are we going to do next? That's in the next lecture. What we're going to do is now take this neuron, we're going to add the loss, and we're going to train on a simple regression problem. Okay. So hope you understood from this session and learned how to set up a neuron and how a neuron basically works. And then we'll see you on the next one.